Hey guys, Mr. O'Sullivan here. Hey, we are continuing on talking about the worked out solutions for the Unit H test. And this recording is for question 2. And so we dive in here. We're given a slope field that for the differential equation dy dx is equal to 1/16 y times the quantity y squared minus 9. So there's our differential equation. Here's our slope field and stem of the problem. So our differential equation has the slope field shown above. Let y equals fx be the particular solution to this differential equation that passes through the point 3, 1. Okay, so that particular solution that goes through this point right here at 3, 1, we are calling f of x. Okay. Okay. And then we're asked to answer 4 questions based on that differential equation and that slope field. All right, so part A, holy mackerel. Use the line tangent to the graph of y equals f of x at x equals 3 to approximate 3.2, f at 3.2. Wow. Okay, so this one is right in our wheelhouse. So first thing we want to do is come up with our tangent line equation. And so we've got our point of tangency is going to be given as 3, 1. So really I'm starting out like I always do with the tangent line, point slope form. Y minus y1 is equal to m times the quantity x minus x1. I'm dropping in my point of tangency, so I'm dropping in 3 for the x1, and I'm dropping in 1 for my y1. So y minus 1 is equal to, okay, now my slope, m, is really going to be equal to my differential equation such that x equals 3 and y equals 1. Well, if you look at the differential equation, it's only in terms of y. There's no x value in it. So I just have to substitute in, it's 1/16 times 1 times 1 squared minus 9. Okay, so I'm going to save time and I'm just going to drop that in for my equation. Okay. Okay, so again, I'm just going to drop what I just calculated right in there. That's my slope. Now I'm not going to simplify it. I'm not going to run the risk. All I'm going to do is just mess it up. So I'm just going to leave it like that. Okay, so that is my tangent line equation. And now what I'm asked to do is use that to approximate f at 3.2. Okay, so I've just got to actually do 2 things. First thing, I need to get the y by itself. So I'm adding 1 to the other side of the equation. And then the other thing is I want to insert 3.2 for my x. So I'm just going to write this, y is equal to 1/16 times 1 times 1 squared minus 9 times 3.2 minus 3, don't forget, plus 1. And I'm done. That's my approximation. If I want, I can write approximately, using the approximation symbol, approximately f at 3.2. I don't want to use an equal sign there. I want to use approximate. Okay. Okay. Part B, find d2y over dx2. That's just the second derivative. And then use that as your answer in part A, an underestimate or an overestimate, justify your response. Okay. Well, to find the second derivative, I just need to take the derivative of the first derivative. Okay, so I'm just going to set this up. d2y over dx2 is going to be equal to d dx, taking the second derivative of what dy dx is, dy dx. And I'm just writing that out. 1 over 16y times y squared minus 9. Okay, if I just if I just dive into that the way it's written right there, I'd have to use product rule, okay? Which, you know, if, I don't mind it. I'm not afraid of the product rule. I like product rule as much as anybody. But if I can just kind of do a rewrite to where I could just have to use power rule and chain rule, I'm good to go. So what I'm going to do, I'm just going to rewrite the right side. So I'm still doing ddx, okay? But now here's my rewrite. I'm just going to like distribute that over that quantity. So that's going to become, I'm going to write it as 1/16 y cubed minus 9/16 y. Okay, you see that rewrite? Okay, now I have to take the derivative of that. So I'm just doing power rule. So that's going to be just that first term, exponent times the coefficient. Change colors here to keep your attention. So that's going to be 3/16 y squared. But then don't forget, I'm doing the derivative with respect to x. My variable is y. So I've got to do chain rule times the inside function, derivative of that, which would be, yeah, baby, dy dx. Okay? And then second term, ddx of negative 9/16 y is going to be negative 9/16 dy dx. Okay? That is my second derivative. Now, what I'm going to do is I want to, I'm just going to make this, I could kind of run with it the way it is, but that's the second derivative. And they didn't say find the second derivative only in terms of x and y or just y. So what I've got right here is okay, because it's in terms of y and dy dx. But now they're going to ask me, is my answer in part A an underestimate or an overestimate? Well, what I really need to do is I need to drop in and find dy d2y over dx2 such that, and now what I'm looking at is my point of tangency. That was my x equals 3 and y equals 1. And again, I'm just kind of noticing here, I don't have an x in the whole place. I've got, so I'm just going to rewrite this. It's going to be 3/16 times 1 squared. Okay, now here, my dy dx, such that x is 3 and y is 1, that's what I had right up here. Okay, so I'm just gonna copy that down, what I've got. I guess, you know, since I'm doing this mad mess, and rather than having to copy this, I will simplify. I'll go against my better judgment. So 1/16 times 1 is 1/16, and then 1 squared is 1, minus 9 is -8. So this simplifies down to 1/2. Okay, so that's what I've got for the dy dx. So I've got 3/16 times 1 squared times -1/2 minus 9/16 times dy dx again, -1/2. Okay, well, I do have to simplify this out because I got to just, all I care about is this expression negative or is it positive? Okay, well, if I'm looking at this, that's going to be equal to, I'm looking at the first part here, that's going to be equal to negative 3/32. Okay, because my 1 squared just kind of goes away. Don't forget that negative. So 3/16 times 1/2, 3/32, negative 3/32. Okay, now plus the second part here. Okay, it's plus because my two negatives there cancel out and make it positive. This is going to be 9/32. Whoa, okay, well, I see right there, hey, my second derivative is positive. So I'm going to say, because d2y dx2 such that x equals 3, y equals 1 is positive. Therefore, I'm basically saying f is concave up, and therefore the estimate in A is, and here's where I just draw, okay, that's concave up, draw a tangent line, and doesn't matter which direction I went, that tangent line's an underestimate. The estimate in A is an underestimate. Okay? And that's my justification. Because my second derivative is positive, therefore f is concave up, and therefore any tangent line approximation where my function is concave up is going to be an underestimate compared to the actual value. Sweet. All right. Part C says evaluate the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. Justify your answer using the slip field shown above. I just kind of copied it down below. Okay, so this first one, the limit f of x as x approaches infinity. Well, to find that, I'm going to go to my slope field. I'm going to go on to that point there at 3, 1. And now as x approaches infinity, I'm going to the right. So I'm basically just kind of following my slope field. And it looks like I've got a horizontal asymptote where? At x equals 0. I'm sorry, y equals 0. Okay, so that is going to be the answer to this limit expression. Okay, so all I did is I just kind of like went to my point, and then I went to the right because x is going toward positive infinity. Not bad. It's not tough. So the next one, the limit as x approaches negative infinity of f of x. Well, again, jump on the point 3, 1. And now what I'm doing is I'm going toward negative infinity. So I'm going this direction. When I do that, whoa, I've got another horizontal asymptote. This one looks like it's at y equals 3. So that is the answer to those two limit expressions. As x goes to positive infinity, the function approaches 0. And as x approaches negative infinity, the function approaches 3. Okay? Notability, you're killing it. Okay. Part D, last question on the test. Which initial conditions, y at 0 equal k, lead to particular solutions that are increasing? So I'm looking for particular solutions that are increasing as x approaches infinity. So I'm saying as x approaches positive infinity, and then I got to justify my answer. Okay, so I'm going back to my slope field, and I'm looking at, they're asking me really for initial conditions. Well, they're telling us in the initial condition that x is equal to 0, and they're basically saying what is the corresponding y value of those initial conditions. So that means the initial conditions have got to be somewhere on the y-axis. So somewhere along here is where we're placing these initial conditions. Okay, so we know the x-coordinate's got to be 0, but now we're asking, okay, what's the corresponding y-coordinate, and where can we place that point on the y-axis such that the particular solution, as x goes to positive infinity, x goes to the right, will be increasing. Okay, well, I just kind of like drop some on the y-axis. Well, if you look, any one of these that I put above y equals 3, you know, if I drew that, and as all I care about is as x is approaching positive infinity going to the right, you know, these would go like that. You know, and if I put, you know, like one right there, see, so I mean, those would be particular solutions that would be increasing if they had that initial condition. Anywhere where k is what? K is greater than 3. Okay, so that's going to be, I'm just going to put this, k is greater than 3. And then let's see if I got, you know, now if I come below this line, y equals 3, what if I put like one right here? Well, as x approaches positive infinity, I go to the right, I'm following my slope field up, and it looks like they're all coming down this way. So my functions would not be increasing, they would be decreasing. Okay, here they were increasing. Okay, and so nothing from there, but now check it out. If I go below y equals 0, if I go below the x-axis, but I stay above y equals -3, like right here, check it out. My function is increasing. Hey, it eventually flattens out, but I don't care. It didn't say, increasing. I guess I shouldn't say that too. It eventually flattens out. Well, it doesn't really, because I mean, again, it's growing toward y equals 0, but it continues to grow toward y equals 0 as x is growing infinitely large. So really, you know, I'm just drawing it, and it looks like, yeah, it flattens out, but it's still getting closer and closer, but they're increasing. Okay, so again, I'm looking kind of to the right there. So that would be when k is what? K is greater than 0, and k is going to be easy, Tiger. Got stumped there for a second. How about k is greater than -3? And k is less than 0. Okay? And my justification would just be, you know, for this, based on the slope field, you know, with that initial condition, the particular solution as x approaches infinity increases. That's our key. And we would say those would increase without bound. They would go toward positive infinity. They just keep going and going. Those that are above where our k is greater than 3. These that are in between -3 and 0, same thing based on the slope field. The particular solution increases, again, that's the key, increases to, it's going to increase basically to a value of 0, to 0. Okay, but it would still would increase. Both of those increase. Okay. All right, guys. There you go. Hope that helps. Thanks.